Hi, this is a short video I'm recording about exercise 15. This is one where you had to do address translation with a two-level page table. I made up another, so you got to do 5 problems on the exercise. I made up another little problem here that I thought we could talk through. Here's an address that I made up, and let's pretend we wanted to read from that address. Now, on this system, pages are 8 bytes long. 8 bytes is 2 to the third addresses. So that means if we look at this address, we can think of it as 3 low order bits that are offset within a page, which byte you want within a page, and then the rest of the bits, the 6 high order bits, would be page number. Which page is the process trying to access? If we had one big page table, this would be pretty easy. We've got 6 bits for page number, so that table would have 64 entries. And looking at those high order 6 bits, that's binary for 46. So we would just look at line number 46 in that page table, and that would tell us the frame containing the page that we want. But with a hierarchical page table, this page table, oops, I made up a mistake at the bottom here. That should say part 7. But this page table would be broken into page size pieces and each piece we're pretending would contain 8 entries from the page table. So for a page table that started out with 64 entries, that would be breaking it into 8 pieces, each of them containing 8 elements of the original page table. We're going to need a outer page table or a level 2 page table to keep up with where each of these pieces is stored. And since we've got 8 pieces, that level 2 page table is going to have 8 entries. We're pretending, or really I've worked out this problem so that that still fits within a single page. So if we think of the page number as a 6-bit number, of those 6 bits, 3 of them we're going to use to look up a line in the outer page table. That'll tell us which piece of the page table we want. And then the next, I hope I said that right, the first 3 bits we'll use to look up a line of the outer page table. And then that tells us where one of these parts of the page table is. The next 3 bits will tell us which entry we want out of that piece. And then that entry will tell us the frame containing the page of the process that we want. So starting with the top 3 bits, if we go look at the outer page table in this example, this was in frame 10. So here's a copy of frame 10. And those 3 high order bits tell us we want line number 5 out of that. So I highlighted that in red here. There's a figure from the exercise that says how to read this. So every entry of the outer page table has a valid, invalid bit, and then 3 bits aren't used, and there's a 4-bit frame number. So if we look at line 5 of the outer page table, again, we picked that because the top 3 bits of the address tell us whatever you want, the page you want, is described in part number 5 of the page table. It's broken up into 8 pieces. We need part number 5, and line 5 of the outer page table tells us where it is. Looking at line 5, the high order bit tells us whether it's valid or not, and this one's marked 1, so that entry is valid. The low order 4 bits, according to the figure, those tell us the frame where this page lives, and in binary, that's 1011. That's binary for 11. So if we go look at frame number 11, this must contain a piece of the page table. It's got 8 entries in it. Which of those do we want? Well, if we look at the next 3 bits of the logical address, that tells us which line we want out of that piece of the page table. The next 3 bits are 110, and that's binary for 6. So I highlighted line number 6 here. It's same here. We've got a figure from the exercise that tells you how to read this. We've got a valid bit and a read-only bit, and then a 4-bit frame number. So if we look at line number 6 of this piece of the page table, the higher bit tells us it's valid, so we can use that. The next bit tells us it's not read-only, so we could write to it. Doesn't really matter because this is a read operation, so we're not even trying to write to it. So the next thing we care about is, well, where's the page of the process that I'm trying to access? And the low order 4 bits give us that. That's 0110, that's binary for 6. So if we go look in frame number 6, here's a copy of that. That contains one of the pages of the process. So every page is 8 bytes. These are 8 bytes of the process, of the memory of the process. Which of these do we want? Well, that's the last 3 bits of the logical address. 101 for the last 3 bits. Again, that's 5 in binary. So I've highlighted line 5 here. Over on the left, that's its physical address. So we're pretending we've got 128 bytes of memory, and that's just the number for this particular byte. And on the right, that's the contents of the byte. So the byte the process is trying to access contains, I won't read the bits, but I'll point to them, contains that value. And if we wanted to finish translating the address, we started with this 9-bit address. We did 2 levels of page table lookup, and that took us to physical address 0110101. Really the same thing that's listed here. So address translation resulted in a physical translated logical address to this particular physical address. Hopefully, if you had trouble with that exercise, that'll make sense, and it might let you go back and try some of the examples from the exercise again. I think that explains how you could have done this. Hopefully that makes sense. Good luck on the exam.